Welcome to Suchitra's statistics classes. Today we are going to discuss fitting of a binomial distribution and some problems relating to binomial distribution. So let us first discuss fitting of a binomial distribution. Let small n independent trials of a Bernoulli sequence constitute one experiment, and let this experiment be repeated capital N times. That is, a binomial experiment is repeated capital N times. Then we can classify the capital N experiments into experiments with 0 success, experiments with 1 success, experiment with n successes, etc. The probabilities corresponding to the values 0, 1, 2, etc. n and expected frequencies are obtained as follows. From this table, we can calculate the value of f of x and n into f of x for the different values of random variable x varies from 0 to n, where n into f of x is the expected number of experiment. P is obtained from the formula. Mean is equal to summation over x into f divided by summation over f, which is equal to np. And n is very well known from the experiment itself. N is this, and we can calculate x bar, that is mean x bar, which is np. And what is f of x? For a binomial distribution, f of x is ncx, p raised to x, q raised to n minus x. So for x equal to 0, f of x is q raised to n. For x equal to 1, it is nc1, p q raised to n minus 1, and so on. For n, f of x is p raised to n. Then let us do one problem in fitting. 7 coins are tossed and number of heads noted. The experiment is repeated 130 times and the following distribution is obtained. Fit a binomial distribution assuming coins are unbiased and the nature of the coin is not known. So let us do the case 1. The coins are unbiased. In this table we have number of heads 0 to 7. So we know that n is 7. And frequency, total frequency is 130. So capital N is 130. Now we have to calculate f of x and n f of x. For that one, we have to calculate P first. When the coin is unbiased, we know that P is equal to Q equal to 1 by 2, that is 0.5. And N is 7 in this case. And we know that f of x is ncx, p raised to x, q raised to n minus x. Here, that is ncx, 0.5 raised to 7. This table gives the values of f of x and expected frequency 130 into f of x, that is capital N f of x. That is the expected frequencies. And these are the calculated value of expected frequencies, and we know that frequencies are whole numbers. We will adjust these numbers such a way that the total is 130. Then we are getting the frequencies as 1, 7, 21, 36, 36, 21, 7 and 1. These frequencies are called observed frequencies and these frequencies are called expected frequencies. Let us move to the case 2. If the nature of the coin is not known, we have to calculate P from mean of the data. Mean is NP, therefore P is NP by N and Q is 1 minus P, and we know that N is 7. This table gives the value of summation of f of x. So mean is equal to summation x fx divided by summation of f, that is 3.4538, that is NP. So P is 0.4934, Q equal to 0.5066. Now proceed just as the case of 1. You can easily fit the binomial frequencies. Remember, you have to adjust the frequency such a way that total is 130. Next problem is comment on the statement. The mean of the binomial distribution is 10 and its standard deviation is 4. We know that mean is equal to NP equal to 10 and given that standard deviation is 4. And we know that variance is standard deviation square, so it is 16. And it is again equal to NPQ. Divide variance by mean, that is NPQ by NP, you are getting the value Q. So Q is equal to 16 by 10, that is 1 by 6. Q is a probability, it cannot be greater than 1. Here Q is greater than 1, so it is not possible. So what's the conclusion? So the statement is false. If x follows Bn1p and y follows Bn2p and x and y are independent, show that the conditional distribution probability of x is equal to small x divided by x plus y equal to n is equal to n1cx n2cn minus x n1 plus n2cn. Given x follows Bn1p and y follows Bn2p and x and y are independent. Therefore, we know that z is equal to x plus y follows b of n1 plus n2p from the additive property of binomial distribution. Therefore, p of x equal to small x given x plus y equal to n is p of x equal to x comma x plus y equal to n divided by p of x plus y equal to n. That is equal to p of x equal to small x. Here we have capital X. When we are applying small x to the capital X, so we can rewrite y as n minus small x divided by p of x plus y equal to n. That is equal to p of x equal to x into p of y equal to n minus x divided by p of x plus y equal to n, since x and y are independent. Expanding, we will get this expression n1cx p raised to x q raised to n1 minus x n2cn minus x p raised to n minus x q raised to n2 minus n minus x divided by n1 plus n2cn p raised to n q raised to n1 plus n2 minus x. Combine the p's, q's. We can cancel all the p's and all the q's. The result is n1cx n2cn minus x divided by n1 plus n2cn, which is the required result. The next problem. Suppose the moment generating function of a random variable x is of the form x t equal to 0.6 plus 0.4 e raised to t all raised to 8. What is the MGF of the random variable y equal to 3x plus 2 and evaluate e of x and v of x. We know that if x follows b and p, mxt is q plus e raised to t all raised to n, that is x is a binomial variate. Comparing this mxt and the given thing, we will get q equal to 0.6 and p is 0.4 and n equal to 8. Therefore, E of x is np equal to 3.2. V of x is npq is equal to 1.92. And we know that m of ax plus bt equal to e raised to bt mx at from the properties of moment generating function. So, m 3x plus 2t is e raised to 2t mx 3t. That is e raised to 2t into 0.6 plus 0.4 e raised to 3t all raised to 8. Next problem is x follows the binomial distribution with the parameter n equal to 6 and p. If 9 into p4 equal to p2, find p. P of 4 equal to p of x equal to 4 equal to f of 4 equal to 6c4 p raised to 4 q square. P of 2 equal to p of x equal to 2, that is f of 2 equal to 6c2 p square q raised to 4. And given that 9 into p of x equal to 4 equal to p of x equal to 2. Apply the expansions, cancel the like terms. We know that ncx is equal to nc n minus x. Using this result, we can write 6c4 equal to 6c6 minus 4 equal to 6c2. So, we can cancel 6c4 and 6c2. Therefore, we have 9p square equal to q square. Solving, we will get the values of p as p equal to 0.25 and minus 0.5. Since p is a probability, it cannot be a negative number. So, the possible value of p is 0.25. The next problem is the mean and variance of binomial variate x are 16 and 8. Find p of x equal to 0 and p of x greater than or equal to 2. Mean is 16, variance is 8. Therefore, np is 16 and npq equal to 8. Therefore, variance by mean is equal to 0.5, which is equal to q. Therefore, q equal to 0.5, p equal to 1 minus q, that is again 0.5. n is equal to np by p, that is equal to 32. Therefore, f of x is ncx p raised to x q raised to n minus x is 32cx 0.5 raised to 32. P of x equal to 0 is 0.5 raised to 32. P of x greater than or equal to 2 is 1 minus p of x less than 2 is equal to 1 minus p of x equal to 0 or 1 is equal to 1 minus p of x equal to 0 minus p of x equal to 1. That is 1 minus 33 into 0.5 raised to 32. Then let us have a measures at glance of a binomial distribution. So far we have studied from part 1 to part 5. If x follows b and p, f of x is ncx p raised to x q raised to n minus x. Mean is np, variance is npq, standard deviation is root npq, moment generating function is q plus p raised to t all raised to n, characteristic function is q plus p e raised to it all raised to n, beta 1 is q minus p whole square by npq and gamma 1 is q minus p divided by root npq, beta 2 is 3 plus 1 minus 6pq by npq and gamma 2 is 1 minus 6pq by npq. Recurrence relation for central moments is this. Recurrence relation for row moments about 0 is this one. Recurrence relation between binomial probability is this one. From this recurrence relation for central moments, we can calculate central moments. From this one, we can calculate row moments. From this one, we can calculate probabilities of a binomial distribution. Mod x lies between n plus 1 into p minus 1 and n plus 1 into p. If n plus 1 into p is an integer, we have a bimodal class. If n plus 1 into p is not an integer, integer part of n plus 1 into p will be the mod. So what are the things to be known? How to fit a binomial distribution, understanding the measures of binomial distribution. For that one, try to do a mathematical model, calculate NNP, using that NNP calculate necessary characteristics. Thank you for watching. If this is found to be useful, then like and subscribe Suchitra's statistics classes. Once again, thank you.